thanks so much for having me here. I feel like I'm amongst friends tonight because probably explain my most recent career has been in aerospace and moved into the world of nuclear a couple of years ago to join this amazing project. And I've been on quite a steep learning curve, going back to textbooks and then the nuclear aspects. Yeah, if there's any nuclear scientists in the audience tonight, just go on those aspects. But I'll give a presentation and take you through some of the aspects of the program that we're working on, and there'll be plenty of time for a Q&A at the end. You'll soon realise that this is a very early stage development program for us at Rolls-Royce, so I'll learn as much from the Q&A sessions as I'm sure you will. Look forward to that. Yeah, just a vision up front, I guess. We'll get into some of the applications, but this is a vision for the micro-reactor in its installation for a nuclear electric propulsion application, just to give a kind of vision for what we're talking about. We'll get into the technology a bit later on. But this is the kind of vehicle that's being proposed for Moon to Mars missions as part of the Artemis program and beyond. And the use of nuclear power is particularly the further away from the sun you get, is seen as a real key enabler for those kind of missions. We'll talk a bit more about that later. Just show my slides here. Yeah. So what we'll do, we'll talk a little bit about our program, then I'll expand out to talk about general applications of micro-reactors. This is quite an interesting backstory and an emerging sort of market at the moment. We're going to talk a little bit more about the specific technology behind the micro-reactor and some of the key advancements that are happening right now. And then I'll just conclude the presentation with a few slides on career opportunities at Rolls-Royce for those that are interested in that. But yeah, really great to be here to talk on behalf of the team and also on behalf of the company. Rolls-Royce has got a long history of collaboration in the aerospace sector around the Solent. In fact, our co-founder Charles Rolls, as many of you know, he actually died in a flying accident at Hengistbury Airfield, which is just along the coast from here, down towards Christchurch back in 1910. But it's really his pioneering and entrepreneurial spirit that formed the basis of the culture of the company that still exists today, and we're very precious about that. Hopefully you'll see some of that come through in the presentation and some of the work we've done on this project. And in a world where things seem to be increasingly difficult and complicated and expensive to achieve, that's something that we try and hold close. Yeah, and moving into the interwar years, this is a picture of the Supermarine S6B seaplane that was designed and built just across the Itchen from here and competed in the Schneider Trophy races that happened in the late 20s, early 30s. Rolls-Royce designed an engine for this aircraft called the Rolls-Royce R, and the technology behind that engine then went on to form the engine family that became the Merlin and the Griffith later on. So yeah, that was that period of aerospace innovation was really critical for the years that followed. And that's kind of a typical model for the way innovations happens right now. And we very much feel like we're in that phase for micro-reactor at the moment. So bringing this a little bit more up to date, this is a project we concluded a couple of years ago to make a demonstrator for electric flight called the Spirit of Innovation. And a lot of echoes here with the Schneider Trophy aeroplanes that raced around the Solent in the interwar years. In the sense that this aircraft was specifically built to break the world speed record for electric flight, which we did. There was no compromise there. It was built specifically for that mission, very short mission to go very fast. Our chief test pilot, Phil Dell, had to go on a crash diet to build this side of the volume. But actually, people think about Rolls-Royce as being a big engineering headquarters out north in Derby and out west in Bristol. But all of this work was done at Boscombe Down Airfield, which is not too far from here up in Wiltshire. Okay, and the University of Southampton is particularly important to us because it hosts one of our 28 university technology centres. These are centres that we set up globally to tap into the latest academic research and innovation. So the centre here at Southampton looks after automation methods and design methods for us, which is particularly important to me as the Chief Design Engineer, obviously. You can see some examples of recent research there that we've been able to do in Southampton and pull into our development programs within Rolls-Royce. This is a really important part of the Rolls-Royce operating model, right? We are a company primarily based on bringing innovative products to market, so our ability to link into academia in different specialist areas and pull that through is really vital to us. So we're very grateful to the University of Southampton for the support we get here. And if any of you are interested in that as a potential opportunity, please come and talk to me afterwards, or to Andy Keane or David Toll, who run the UTC for us. There are actually some examples of pieces of work that their team have done on this project for us, which I'll show you later in the presentation. Okay, so onto our programme then. Here we're talking about Rolls-Royce, the global power systems company, not the car company. Famous for aerospace products, particularly derived from the jet engine. As you heard from Trevor, I spent many years working on the A350 programme prior to this. Fantastic aircraft, and if you're ever travelling up the A54 and M3, you'll see those trucking down to Portsmouth to take the ferry across to Toulouse. And that programme has been a real success for us in the world of aerospace. The production rate on the A350 programme is something we've never seen before, up to an engine a day or two. So apologies if you get stuck behind one of those on the motorway. They're pretty big units. Relevant to this project is we have a division called Power Systems, which is based in Germany. They do, their background is in compact high-speed diesels for different applications. So they're evolving into advanced fuels like hydrogen now, and also moving outwards into microgrid design and bringing in different elements of microgrid solutions. And as you'll see, that's, I guess the micro-reactor could be considered as just another power element in a microgrid solution for a particular customer. So one of the great things about this project for me is that I get to tap into different bits of expertise around the Rolls-Royce Group and try to bring those together into the programme. We'll talk a little bit about SMR in a minute, because that is relevant in the overall product range. We'll come back to that. What a lot of people don't know is that Rolls-Royce are the technical authority for the nuclear steam raising plant in the UK submarine fleet. This is a role that we've had ever since the beginning of the nuclear submarine programme over 60 years ago now. It's quite unusual actually to have the capability to manage the full life cycle of one of these reactor plants in one place. If you look at the way that it's set up in the US, for example, the value chain for the support of their submarine program was kind of fractured. The design was done by the government, and then they issue definition out to the supply chain. But in the UK, within Rolls-Royce, we have the capability to do everything from the concept design through to verification, manufacture, install, support, and decommissioning. And that puts us in the UK and in Rolls-Royce in a really strong position to go after these new markets with new nuclear products. Something that we see as a really big opportunity for us and for the UK in general. Okay, so the nuclear portfolio that we're talking about here is spans quite a broad spectrum of applications. To start from the right-hand side, you've got the gigawatt scale power plants that are grid connected. Hinkley Point C is a relevant example. Rolls-Royce as a group has developed this technology called the small modular reactor, with the view that by reducing the size of any given plant, you can get economies of scale through the production process and modularize the production of those and to bring the overall cost down. That team is a separate venture within the Rolls-Royce Group to us, so we talk to them and they share knowledge with us, but they're a kind of different project. And you might have seen in the news recently we've had some success in winning a partnership into the Czech Republic, which is a really big step for them and moving that forward. Again, as a proud Brit, I guess that's a really good thing, I think, for the country to be doing and moving forward with. So in the range of the portfolio here, the submarine sits somewhere in the middle there. Obviously, the power is actually classified, but it sits somewhere in the middle. And then beneath that, we have these range of applications that we call micro-reactors and advanced modular reactors. Now the terminology here is a little bit, within industry there's a little bit of debate about exactly how big or small a particular type of reactor is, but this is the way we classify them. So in the 10 to 100 megawatt per unit range you've got advanced modular reactors, and these, because of the size, these tend to be permanent installations. But we see an increasing demand for those for different things, as we'll see in a minute. We've then got a deployable and redeployable terrestrial micro-reactor solution. So you can imagine a small plant with an ISO container volume that can be shipped around, deployed and redeployed. Yeah, that certainly seems to be an emerging demand as well for some applications we'll talk about. And at the bottom end is the space market, which sounds crazy, right? And as someone who's spent a career working on I guess first ship propulsion and then aircraft propulsion. This is a real venture into new territory for us, but there is a genuine demand for that, and we'll come on to why in a bit later on. So here's a vision for the deployable, redeployable micro-reactor. Just to give you a bottom line up front, I guess. So in this application, it's been used in a mine where they need power close to the end use, and the mine will evolve over time and move around, and the use of the power will move location. So actually having something that you can pick up and move around is quite attractive to those kind of operations, particularly in areas where they're off-grid and they don't have access to grid power. Can really help out with the logistics supply chain compared to a diesel genset, which is the kind of incumbent technology where they have to ship the diesel in over a long distance. We live in a time where there seems to be a bit of a perfect storm of imperative building a case around these kind of products. So I guess from the point of view of the environment, we talk to a lot of customers who are genuinely interested in the journey to net zero, which is great, right, for our generation. It's a really important aspect of anything we develop. And we do see people coming under genuine investor pressure now to demonstrate a route to net zero. Nuclear will hopefully play a part in that. It's not the whole solution by any means, but I think a lot of people see that it could be a solution to some of those challenges. The second aspect is around the development of technology. So, as we'll talk about later, some of the key underpinning technologies that allow the miniaturization of the reactor are coming to the fore and are going through their qualification process at the moment, particularly the fuel technology we'll talk about. So that's the second part. And the third part is, in general, the development of what industry calls Generation 4+ reactor technology. That's moving on from the pressurized water reactor technology we're familiar with, towards novel technologies that offer an improved level of what we call passive safety. I'll talk a little bit more about what that means later on. But those three things are coming together at the moment. I mean, suddenly there's a lot of interest in this market, and we do see that. So part of my role, as well as trying to design the thing, is to meet customers and help them understand what it can and can't do. And it's a really interesting environment to be in. Picked out, I won't go through all of those on the right hand side there. I'll just pick out a couple of really interesting use cases that we see. Clearly data centers is a really fast growing area at the moment with AI. I'm sure that you'll have seen this in your course as well, but the demand for AI has massively increased the amount of energy that the data centers need, to the extent where even in developed kind of economies, the grids can't support the level of growth they're looking for. So they kind of are looking at some of these other solutions that can give them resilience of power where they're not dependent on the national infrastructure to be able to support their growth, which is kind of interesting. Similarly, we do see other examples of industries that are looking for off-grid power for other resilience reasons. Maritime's an interesting one. Quite a conservative market traditionally, but one of the sectors that is really challenged by the journey to net zero. We talked to some of the operators in the maritime sector at the moment, and there isn't really an obvious solution to get to an acceptable emissions position. So nuclear is one of the options that's being considered. Obviously for maritime there are some real challenges there around the regulatory environment with ships moving from one domain to another all the time. That's really interesting for us, both from a sort of a traditional power propulsion point of view, but also in the wider infrastructure. So when people talk about these advanced fuels like hydrogen, actually there's an awful lot of energy involved in manufacturing hydrogen and some of these advanced fuels, as I'm sure you're aware. So when people talk about the hydrogen economy and the overall kind of ecosystem that's required, the availability of nuclear power in situ to be able to manufacture some of those fuels is quite interesting to people. And that kind of links into one of the other applications as well around industrial processing and chemical processing, where you've got really energy intensive processes, particularly where they are remote, and you can with a reactor you can buy 10 years worth of fuel in one go and not have to refuel it in the way that you do at the moment with a diesel genset or other power sources. So hopefully that makes sense. We'll talk a bit more specifically about the space applications. I've got some more detailed slides on those. And like anything with nuclear, it was tried in the 60s, right? So there were a number of applications here of micro-reactors that were developed during the 1960s. And there's a lot to learn from these, although the technology has obviously moved on a long way since then. On the left-hand side here, you've got a couple of examples from the US Army's nuclear power program. The ML1 was an example of what we call the redeployable micro-reactor. And that was demonstrated on the Idaho National Lab test range. But at that point, the US was in the middle of the Vietnam War, and oil prices crashed. So the attractiveness of that technology went away, and that program didn't get any further than testing a demo unit. The PM2A is another reactor from that program. That was a much larger plant and not redeployable in the same way. But it was actually, they deployed one of these to Antarctica to power the research base down there. Another example of remote power and making them a bit more resilient to the logistics chain of getting fuel to the base. SNAP 10A is the only example of a Western fission reactor that flew in space. That was flown in 1965 and orbited for a while and unfortunately failed due to an issue with another aspect of the payload, and that program stopped after that. But you can go into a great Wikipedia black hole reading about all the different space applications in the Cold War era, and the Soviets in particular had a number of different designs that they flew successfully during that period. On the right hand side here, this is the NR1. Again, there's a great book about the NR1 if you're interested in this kind of thing. NR1 was a submarine that was developed by the US Navy and Admiral Rickover in the 1960s for a very specific mission to explore the seafloor, and ran for many years. You see there, it was quite an extraordinary lifespan for a reactor plant up to 2008. That kind of falls into the category of a micro-reactor. It's a very small plant that can be operated by a single operator from that person. So there's nothing new in nuclear, and there's a lot we can learn from these programs, even though things have moved on a long way. And it just goes to show that the reason that some of these programs didn't succeed wasn't necessarily due to the technology at the time, but it was due to the economical situation, the macroeconomical situation they found themselves in, and the way that things evolved. Right, so this is a slide about Project Pele. Project Pele is the US's program to develop a redeployable micro-reactor solution. And this is really exciting. Our colleagues at Rolls-Royce North America are involved in this project. They're designing and supplying the power conversion subsystem. I'll explain that in a bit. I was over at the plant a couple of weeks ago where this is being assembled right now. So this is a live program, slightly later than they'd hoped, I think, but it's due to go critical in the Idaho test range next year or the year after. And we all kind of hope, if that's successful, that will really open people's eyes up to what's possible here, and particularly in the US command structure, the possibilities that can be achieved with this kind of technology. So that's the US side of the program, and we have an equivalent design program in the UK at the moment on that scale of plant as well, and with a similar objective. Right, so let's talk space. This is a vision, I guess, of the micro-reactor for the lunar base as part of the Artemis program. And I'll show the slide first because it gives people a picture of what it looks like and what we're trying to achieve, and talk about some of the key aspects. So it looks really strange, right, in the sense that it looks like it's going to fall over, but of course very low gravity on the moon, so not so much of a concern. The big thing on the top is that the petal-shaped arrangement is actually the radiator, and of course on the lunar surface there's no way to get rid of waste heat other than through radiation, so the radiator is a key part of the design. And actually when we look at the total payload, the radiator is the biggest and heaviest part of the overall payload. So a lot of the system engineering work we're doing at the moment is to try and optimise the overall design to minimise the size of the radiator. Just to talk about a few other things, techie requirements, I guess. So as I'm sure you're aware that the Artemis mission is primary objective is to establish a permanent human presence on the moon, and the lunar nighttime is 2 Earth weeks long. So for the astronauts to be able to do their science during the lunar nighttime, they're going to need some kind of power solution that is not dependent on the sun. Also, the location we're planning to explore in the Artemis mission is at the lunar South Pole. And the solar resource at the lunar South Pole, because the angular incidence of the sun is quite poor. So when you look at the design for some of the solar panel solutions that they would need, they're really big and kind of unfeasible. So the actual kind of mission architecture is still being evolved by NASA at the moment. But their view is that certainly as the lunar infrastructure builds out and they want to establish that presence over the lunar lifetime, they're going to need another source of power like the micro-reactor. Yeah, other challenges on the moon. This thing's been pelted by micrometeorites all the time, right? You've also got the background radiation issue to worry about. So when we talk to NASA HQ about this in the States, their engineers, the number one thing they're worried about is upsets to the electrical systems from solar flare events and background radiation. So protecting against that is going to be tricky. They want it to be able to run for 10 years without any planned maintenance. Right, so if you're familiar with gas turbine design or complex system design, that's quite a challenge for us, and actually drives quite a lot of thinking into redundancy of systems and reliability. And the lunar temperature range is interesting as well, right? So at the South Pole, in a shaded region, the temperature can drop down to almost absolute zero and range up to 40 or 50 degrees C during the daytime when you've got sun impinging on you. So that's quite a significant temperature range to manage when you consider that part of NASA's mission is to go and use a reactor for what they call in situ resource utilization, or ISRU, which is the mining of resources from the lunar surface to be able to manufacture fuel for the mission and other things that allow them ultimately to use the lunar base as a launch pad to Mars. And that's the Moon to Mars architecture which NASA have published in the last couple of years. So it sounds really out there, right? But this is really happening. This program is funded. As you know, the Artemis program is moving forward. We saw the SpaceX launched yesterday, the latest one, and all of that technology is geared towards the initial lunar base and the Moon to Mars mission. Yeah, and this slide may be a little out of date now, but you can see the manifest for the different Artemis missions. So when this slide was produced, you can see here the fission surface power plant was slated for Artemis 5. I think these timescales may be moving out a little bit. But this is actually, I mean, if you think about the challenge we've got here, to develop a new nuclear plant in this kind of timescales is really racy, particularly with the requirements that we've been set. So it kind of drives us as an engineering team to try and think about using very conventional technologies, albeit in a very unconventional environment. Okay, so just to touch on a couple of other applications here for microreactors in space. The first is nuclear electric propulsion, and this is effectively using the reactor as the means to create electricity on the payload. To power a fairly conventional ion thruster of the type that we use today for space missions. And there's different applications for nuclear electric propulsion being discussed. So some of the operators of missions around the moon want the ability to be able to maneuver in areas around the moon where there is no sun. So solar panels don't work, use something else. And then for deeper space missions, as we saw right at the beginning of the presentation, the thought is that nuclear electric propulsion can reduce the Moon to Mars time significantly. So that's something that's being considered as part of that longer term strategy. The next slide shows an example of nuclear thermal propulsion. So this is a very different beast. In this design, you use the reactor core there to accelerate propellant through the nozzle directly. This is a project called NERVA, which was again developed in the Cold War period in the States. But there is a project, a live project called Project Draco, that's been run by DARPA and NASA in the US, to put a nuclear thermal propulsion system into orbit within the next couple of years. And actually, out of all the missions, that is currently the one that's scheduled to launch first, and it's really exciting. It's nuclear thermal propulsion, in theory, is a kind of game changer for deep space missions. it's a higher technology, I guess, in the sense that the temperatures within the reactor core for nuclear thermal propulsion are significantly higher than anything we're considering for the other applications. So in terms of materials technology, cooling technology, that's a really advanced kind of really advanced project. But again, as a UK citizen, I can't see it, but I was at the facility a couple of weeks ago where they're assembling this payload right now, so this is really happening. Yeah, and before I get into the technical slides around our design, I just wanted to say a few words about the level of support we've had from the UK Space Agency in the UK, and also the level of collaboration we see between the UK and the US on these missions. So NASA have been very open that they'll only be able to achieve the Artemis missions through international collaboration, and the UK Space Agency has a key part to play there. So there's a commitment under the Artemis Accords that as a nation will provide a level of value towards the Artemis missions. And the micro-reactor is one of the things that our agency sees as being important to them as part of their contribution. Ultimately, that's about us getting UK boots on the moon, right? A really important strategic imperative, and a great to go to work every day knowing that's something that you hope ultimately contribute towards. Last year, the President and Prime Minister at the time announced this thing called the Atlantic Declaration, which is quite a broad kind of declaration around collaboration on different technologies. But right at the very bottom, and we did have to scroll right to the bottom to make sure it was in there, was the statement around collaboration on space nuclear power and propulsion. And that's fantastic. There's a lot of good work done within our government and within the agency to make sure that was included in the scope of the Atlantic Declaration. And yeah, again, it just shows the direction of travel really, that the UK is serious about supporting this, which is fantastic. Okay, so now we'll talk about some of the technologies then. And this section is not going to go super deep into nuclear science. I hope that's okay. I've got a few equations, but no more than that. But I'll just start with a bit of an overview of the nuclear technology for those that aren't so familiar with it, and then we'll move on to some of the micro-reactor specific stuff. But basically, in simple terms, a conventional nuclear power station works in a similar way to a coal or gas-fired power station, in the sense that the nuclear reactor creates heat through typically a primary circuit. Then you have a secondary circuit that converts that heat into electricity. And it's just the same for a coal-fired power station, except that it's the coal that's providing the heat, not the reactor. Right? The key difference for the nuclear plants is that the fuel is incredibly energy dense, obviously. Right? And so there's some stats there around equivalency between uranium fuel pellet and the volume of natural gas or amount of oil that you need to burn to achieve a similar level of power. And clearly that's if you can get the rest of the technology to work around it, that can enable the miniaturization of the plant down to these AMR and micro-reactor levels. And yeah, one of the key benefits, I guess, if you're in the current environment where people are concerned about their energy resilience and the resilience of oil prices and things like that, you lock in a significant amount of energy without having to refuel it at the same kind of pace. So the designs that people are looking at the moment suggest that you could probably refuel one of these things every 5 to 10 years. And so if you're an operator who is really dependent on oil or gas at the moment, that obviously makes you more resilient. So yeah, cartoon of a typical nuclear plant layout. This is a fairly typical pressurised water reactor arrangement. So on the left in the yellow building there, you've got what's called the reactor island. The green in there is the reactor pressure vessel. So the green circuit takes the heat from the reactor into the steam generators. That green circuit is a closed primary circuit. The steam generators generate the steam, and that gets passed out of the reactor island onto the turbine island, driving steam turbines and the electrical generator. That again is a closed steam cycle, if you like, closed secondary loop. At the back end of the plant there'll be some form of cooling system to take the waste heat away from the water before it goes back into the steam generator. So the condenser there obviously cools the steam down back to a liquid, and the cooling water system takes it out to either cooling tower or maybe even an air-cooled waste heat recovery system. So hopefully that makes sense. It's a fairly conventional layout. When we talk about the fission process, this is the limit of the equation, sorry. But in conventional pressurized water reactors, we typically use uranium-235 as the fuel. So in the reactor, you have your uranium fuel that's enriched, typically at the moment to a low enriched uranium level, which is about 5% uranium-235. You then start the reactor by firing neutrons at that uranium fuel. That initiates the chain reaction by splitting the uranium into different products and releasing other neutrons as part of that process, which then go on to initiate the chain reaction by interfering with other uranium atoms and splitting them and creating the thermal energy. Now, there is a complication there because this is starting to get into the complexity of reactor control, because the timescales associated with these processes are complex. When you create your initial reactor, there's most of the activity happens in what we call a prompt arrival time, so 10 to the minus 5 seconds. But there are also delayed neutrons that come out of that process that have an effect over a longer time period. And so that starts to talk to the complexity of trying to manage a nuclear reaction, because you have sort of an instant effect and then a later effect to be able to have to manage as part of the control process. So as part of this process, you split the atom and you create fission products. And those fission products are the things that you have to make sure don't get into the external environment. We'll talk about safety in a minute, but that's the key thing. So you create your energy through the fission of the uranium-235, create fission products, and you have to manage those later on. So yeah, in the world of safety then, as a designer of a reactor plant, there's kind of three key safety functional requirements that you're concerned with. The first one is managing the core reactivity and the chain reaction itself, because there's obviously we talked about the energy density, the amount of energy that's contained within that nuclear core is very high, and so you have to make sure that chain reaction is under control at all points. Second, and related to that, is the requirement to manage the level of heat generation that the core can produce. And that's typically comes down to making sure that under normal operation and faulty conditions, the reactor core and its surrounding components can never exceed the allowable temperatures of the materials that are and so that's the second requirement. And in the process, you generate the heat for the initial fission reaction, but also there's this effect called decay heat, which happens over an even longer time period, and needs very careful management. So, for example, you might shut your reactor down, and the plant will shut itself down over a time period of a few minutes. But then, actually, as the process continues, it creates this peak of decay heat, and the peak of that heat may occur several hours after the shutdown process. So managing the decay heat as part of the design is really important, and can be a defining load case for the definition of some of the component parts within the design. And the third one, we talked about this a minute ago, the control of the fission product inventory. So through the process of splitting the atom and creating the heat and creating those fission products, you have to make sure that those fission products can't get into the external environment. And we'll talk a little bit more about the design of fuel and how that's managed in these advanced reactors later on. But back to the principle of the Generation 4 reactors, the idea with these reactors is to move away from a position where the failure modes need to be actively managed to a position where the reactor will manage those through design. Yeah. Okay, so here's just an overview of one of our concepts for the space micro-reactor. And just to give you an idea of scale, this thing in real life will be about 3 meters long and about 1 meter in diameter for this equipment. And then also you've got the radiator on top of that, which is the biggest part of the payload of the facility. So in this concept, you've got the reactor core on the left there generating the thermal heat. In this concept, you use high temperature heat pipes to extract that heat from the core into the intermediate or primary secondary heat exchanger. And then you have a secondary circuit that uses an inert gas to extract that heat into a series of turbine units that are connected to electrical generators. So that gives you an idea of the overall layout of the plant. And the studies that we've been doing over the last year or 18 months or so are looking at the trades around some of those technologies and alternative solutions for those. And I'll talk about some of the technological aspects that we can trade in and out of the design. Heat pipes are something that personally I hadn't come across before this project, but apparently we've all got them in our laptops. So coupled water heat pipes are a very common technology used to distribute heat around equipment. And the beauty of heat pipes is that they have no moving parts, right? So when you come back to the reliability requirement we were talking about for the space micro-reactor, no moving parts has got to be a good idea. Basically, what physically this is, you apply heat to the hot end at point 1. That evaporates the working fluid, travels along to the other end where it condenses, sheds its heat, you can collect it from that end, and then the condensed fluid runs down the wick back to the start. If you think about effectively that is then the primary circuit of the reactor. You just have an array of heat pipes that extract heat from the fission process into the back end of the plant. When we studied heat pipes, although they are well-established technology for laptops at low temperature, the reactor temperatures we're talking about for these Generation 4 reactors are much higher. So typically 7 to 850 degrees C, T-hot at the reactor. And the development of heat pipes that can extract that temperature of heat from the reactor core is still relatively low technology readiness level. So you're looking at using a working fluid like sodium to be able to transfer the heat in the heat pipe. There you go. So there's an example of a reactor design from the US called Krusty. And in this arrangement you've got, hopefully you can see that, but at the bottom there you've got the reactor core, you've got these series of kind of golden coloured heat pipes. I guess one of the attractive heat pipes is you can bend them and shape them as well, so they don't have to be straight for packaging. And then in this design, they are transferring the heat into an array of Stirling engines. So Stirling engines is something that have been well developed for these kind of applications by NASA. And if you go out to NASA Glenn at Cleveland, Ohio, they've got banks and banks of Stirling engines pumping well endurance tests to demonstrate the technology for these kind of missions. The issue with the Stirling converter is that when you look at the trade studies, they don't scale up very well to higher powers because of the relationship between the power and the radius means that the machine gets very big very quickly as you scale up the power curve. So typically for fission surface power products of about 10 to 20 kilowatts, they might be a viable technology. But for anything bigger than that, our trade studies show you move towards gas turbine converters, which is obviously our strength and area of interest. The NASA spec at the moment for fission surface power is 40 kilowatts electrical for the total unit. But when you look at their vision for the lunar architecture, that's only going to grow, right? I mean, I guess you'll have seen in the space launch market, NASA are now acting as a visionary, and they're expecting commercial operators to come in and operate the mission, as we've seen with SpaceX and so on with space launch. So same on the lunar surface. So we talk regularly to some of the potential operators up there, like Northrop Grumman, Lockheed Martin, Blue Origin. And when you talk to those people and understand what they want to do on the lunar surface, it involves a lot more power than 40 kilowatts. So part of our challenge is to try to design it to be scalable. Yeah, so one of the challenges with that heat pipe concept is extracting the heat from the cold end of the heat pipe into the secondary system. And here we've done some really interesting work with another one of our university technology centres at Oxford University, where they've historically done a lot of research for us around hot end gas turbine technologies, turbine cooling and that kind of thing. But they've developed a heat exchanger concept initially in designing CFD, but then also validated that with the rig test you can see there to demonstrate how you can effectively remove the heat from the end of the heat pipes. I guess conceptually, the most difficult thing about that concept is trying to get the thermal flow through the cross-section of material that you have in the heat pipes and out again. So being able to do that effectively is really dependent on having a really good heat exchanger at the back end to do that. Okay, so this is another potential space concept, and this is a high-temperature gas reactor concept. This is currently our preferred solution, and in this concept you've got effectively a single loop of high temperature of an inert gas. Obviously our experience is in air breathing engines, so this is from a gas turbine design point of view, this is the ultimate challenge, right? It's a closed cycle, so you've got many degrees of freedom, you can work with your operating pressures, you can pick that. You can pick advanced cycle elements to play with as well, so you can look at intercooling, recuperation, multiple passes, reheat through the reactor core. This is the simplest arrangement here, where you've got the reactor core on the left there, heating up the gas. That then runs through a turbine into a heat exchanger connected to the radiator system, back through the compressor, and into the bottom of the reactor again. So yeah, that's the simplest version of our design, but we love to play around with some of the more advanced elements as well, and we'll see some of that a little bit later on. But I guess compared to the heat pipe design, you've got moving parts now, right? So having a compressor and a turbine running at varying power conditions over the lifetime of this product and being able to assure their reliability is really interesting. And simple things like bearings. We can't have an oil lubrication system on the moon. We can't vent it to atmosphere. So we need to think about things like air bearings and ball bearings to be able to manage the rotating machinery, which is interesting. Just to pick up a couple of other key parts of the functionality here around the nuclear reactor. So within the reactor there, you can see the fuel. That's the red hatch parts in the middle of the reactor. There's a key function within the reactor is the moderating function, and here you choose a material that effectively slows the neutrons down within the reactor core into a range where they interact more readily with the fuel atoms within the core. Traditionally, in a pressurized water reactor, the water provides that moderating function. For the high temperature gas reactor, we have the opportunity to choose other ways to do that, and we'll talk a little bit more about that later on. Then on the outside of the reactor, you've got the drums. You can see those conceptually drawn on top of them. Obviously, this would be a drum-shaped, the cylindrical-shaped core with control drums staged around the outside of it. And the idea there is that you can have a drum that's part of its circumference is coated with a moderating material. Reflecting material, and the other part of the circumference is covered with an absorbing material. So depending on how much of the reflecting material is facing the core, it depends on how many neutrons are bounced back into the core and become part of the reaction. So that's one of the concepts for providing control over the longer time constant. Traditional designs use control rods, and we're very familiar with those from the pressurized water reactor. So there's a debate about whether rods or drums or a combination of the two is appropriate for this design. One of the typical operating issues with control rods is that normally in an emergency scenario you just drop them by gravity into the core, right? So obviously you haven't got the gravity to work with here, so you need an alternative way to assure that that's going to work. Okay. Good. So we'll talk a bit about fuel next. This is a schematic of coated particle fuel. So in a conventional reactor, the fuel is clad in a metallic clad structure. And going back to the critical safety functions we discussed earlier on, there's a lot of work goes into making sure that the fission products can't escape from the fuel through a crack in the cladding material into the primary circuit of the reactor, and then through another failure mode out of the primary circuit into the environment. That's one of the primary things that we have to assure can't happen. The development of this coated particle fuel is really interesting because effectively you can contain the fission products within this poppy seed-sized kernel of uranium. So the orange kernel of uranium there in the middle of this coated particle fuel is the order of a millimetre in diameter or smaller. And then you coat that kernel with different layers of carbon-based material that provide different functions. One of those is fission product containment. Another layer provides thermal resistance so that you can increase the maximum operating temperature of the core. And that's obviously great for thermal efficiency. So as you know, in the overall cycle, thermal efficiency is a function of the hot temperature and the cold temperature. So if you increase hot temperature, you can increase your overall efficiency of the plant. But also gives us more headroom in the failure cases as well. We talked about earlier in that critical safety function of managing the thermal load within the core. If you've got more headroom between your operating temperature and your maximum allowable temperature from the coatings on the fuel, then you have more headroom to manage that. And that's one of the key enablers for this passive safety that I talked about. So coated particle fuel is being developed right now. One of the US companies has just got that through the qualification process and actually tested it in a test reactor. But again, it's not a new thing, and this is actually a UK success story we should be proud of. So back in the 60s, we had a project called Dragon down on the test range at Winthrop in Dorset, which again is not too far from here. And on that site they had a number of different test reactors developing different technologies. This Dragon reactor was a big international collaboration at the time with two primary objectives. One of them was to develop the high temperature gas reactor technology, and it successfully demonstrated that. The second was to develop the coated particle fuel technology, again back in the 60s. And they actually manufactured and tested the fuel all on site down at Winthrop and played around with different designs and combinations of material for the coated particle fuel. I think on the next slide we've actually got a picture here. So this is a cross section through one of the fuel compacts from Dragon. And here you can see the almost randomly distributed coated particle fuel elements inside the fuel compact. Now, I guess it's obvious from looking at that picture, but one of the key bits of science going into these advanced reactors is how to optimise the packing of the fuel within the fuel compact. And from a core density point of view, obviously wrapping the fuel particle in layers of protective material actually reduces the density of fuel in the core overall, because half of the core is filled up with the coatings. So that actually presents a challenge in terms of getting the core density down for some of these smaller reactors. But it's an overall win because it improves your overall level of safety and potentially means you don't have to provide containment structures and concrete buildings around the plant like we do conventionally. So we're currently working with the University of Bangor in North Wales on coated particle fuel production. And it's a good story because this research centre fundamentally was based on a lot of the work that was done as part of Project Dragon a long time ago. But as you can imagine, if you're relying on those coatings to fulfil those safety functions, then you have to be really sure they're going to work. So the team at Bangor have been doing a lot of manufacturing trials for us, looking at different chemical compositions of the coatings to make sure that the binding of the coating onto the fuel particle is robust. And that we can be sure that through the manufacturing process that they're manufactured defect-free, crack-free, that kind of thing. So, yeah, work ongoing at Bangor University and at the National Nuclear Lab on coated particle fuel in the UK. As I say, in the US, similarly, they're probably more advanced at the moment in terms of their development and the fact that they've actually got their fuel through a test reactor. But a key enabler for this generation of reactors. Next is hydride moderators. So we talked about the moderating function a minute ago. If you remember, that's the function of the reactor where we slow the neutrons down to promote the nuclear reaction. Now, hydrogen as an atom is really good at moderating, which is why water's so good, right? But there are alternatives coming to the market at the moment. These advanced hydride moderators like yttrium hydride. are much better than, have a much more powerful moderating function than a conventional graphite core block and moderator. And when we look at the trade studies around the power density of the core, and trying to get the core size down to a size that can enable these smaller applications, the hydro moderators seem to be quite a key technology in achieving that compactness. So yeah, another key dependency there. This slide shows some of the manufacturing trials that we've done on the Space Micro-Reactor under the Space Agency's funding. And I guess it's an important point to make, right, that because of our corporate experience with designing and making these things, we kind of recognise that the manufacturing element is often the hardest part. You know, you can quite easily draw a viable design, but actually being able to realise it is something else entirely. So in a similar way to the University Technology Centres that we were talking about earlier, we tap into the UK's network of advanced research centres like the AMRC and the nuclear AMRC as was. Unfortunately, as you know, that's recently folded, but we have these advanced, the AXRC network as they're known, and they're catapult centres that bring technology from the research environment into a production level. So we talk about the valley of death, I don't know whether that's the term that's familiar to people, but trying to get a technology from the low TRL levels and a laboratory environment into a production ready environment is the hardest part. So getting the technology from TRL 3 to 6 and into a production cell is what these centres are for. So we've done some initial trials on manufacturing graphite monolith block at the top in the middle there. At the bottom there is some manufacturing trials we've done on the reflector material that goes around the outside of the reactor. And on the right hand side there you can see a piece of work that's demonstrating the control drum. Remember we talked about that a minute ago, the thing that's like the yin and the yang with one half of reflector and one half of absorber. So you can kind of see that in the arrangement there. Yeah, and hopefully it gives you an idea of size. So yeah, the Space Micro-Reactor is a pretty small, the actual reactor part is actually pretty small. So one of the control drums is 200 mil diameter and 400 mil long or something like that. It's not a big unit. Okay, this slide talks to unit cost. And this is the piece of work that we did in collaboration with the Technology Centre here at Southampton actually. So Dr. RAeS and the UTC helped us to develop our unit cost model, I guess more relevant to the terrestrial micro-reactor. The space micro-reactor, I think everyone accepts it's going to be quite a bespoke, unique solution. But for the terrestrial micro-reactor, unit cost is going to be really important. The nuclear plant is going to be very expensive up front, but obviously then it pays back over a lifetime because you don't have to refuel and so on. So having a good understanding of that is really important. So what Hacky did was use this software we have called Vanguard that basically builds out structural cost model by breaking down the product into its breakdown structure and assigning cost to each of the elements. And you can do really neat things with a model then, like running Monte Carlo simulations on the cost to look at how variations in different parts of the plant might affect the overall cost as part of our initial cost model. So I guess it's an important point, right? As engineers, we cross the threshold between science and business, and we have to make sure that the product is viable for the market. So getting an early understanding of the cost is really important, and we're very grateful for the work that Hacky did for us here, and that will develop as our project grows. So the final part of the presentation talks to the back end of the plant, and just to introduce this section, I threw up this chart. This is from a well-known gas turbine textbook from Nicholas Cumsey, who's based out of Cambridge and a long-time a consultant to Rolls-Royce. And just to give you an idea, so we talked about the fact that the reactor T-hole will be limited by the core materials and the palette of qualified materials we have for the reactor core, which is quite limited, right? So as the chief design engineer of an aerospace product, we're limited by materials that are aerospace qualified. But for the reactor, especially the space reactor, we've got the additional testing that's required to demonstrate the material can survive the core environment. And if you're familiar with that, there are some interesting material interactions that happen between the nuclear reaction and the chemistry of the material that can cause embrittlement, swelling, all sorts of other effects within metallic materials. So, yeah, very restricted palette of materials to work with in the reactor core. And the process of actually qualifying a new material for that environment is really lengthy. So it might take us 5 years to qualify a new material for aerospace, but it might take 10 or 15 years to qualify material for use in a reactor core. And it makes sense, right? And particularly for civil reactors, they have to go through the codification process, and the regulator is heavily involved in that. So when we talk about the timescales of some of these initial programs, we're going to be looking to use fairly conventional materials in the core, which drive us to limit the core temperature to those material capabilities. As I said earlier, between 700 and 850 C as a maximum temperature. Anything above 800, you're starting to progress into realms of materials that are outside the comfort zone, really. And this chart from Clumsy just shows, for the gas turbine designers in the room, what the turbine inlet temperature corresponds to for conventional gas turbine technology, right? So for the heat pipe core reactor, I've drawn that slightly lower because the heat pipes actually, for material reasons, have a lower temperature capability than the high temperature gas reactor. But even then, the high temperature gas reactor, if you draw that at 1050 K, then in terms of gas turbine technologies, that's the kind of technology we were working with in the 50s and 60s at the dawn of the jet age, right? So on my previous projects on the A350, our engine had a turbine inlet temperature of 2000 Kelvin, and they went into really exotic single crystal alloys with advanced cooling systems and advanced coatings. Here, we're taking a step back in time for the gas turbine we need for the reactor. It's a very different beast. And although it's easier from a materials point of view, it has other challenges associated with it. So here's a schematic of a potential closed Brayton cycle for the back end of the plant. And this is an advancement on the one I showed earlier, which was the simplest version. Right? So here you've got 2 stages of compressor with an intercooler between them. You've got a recuperator at the back end, and you've got 2 passes through the reactor core. And we can do some interesting trace studies on the design to see what benefit each of those advanced cycle elements brings to the overall architecture. And as I was saying at the start, this is a real systems problem. So although you might add significant mass to the power conversion subsystem with the addition of a recuperator, if that recuperator means the overall cycle is 5% more efficient, then the reactor core can be much smaller, and the radiator can be much smaller as well, because you don't have so much waste heat to get rid of. So, interesting system level trades to be done there. And this is a real highlight from the space agency program that we're running at the moment. We actually developed a rig to demonstrate the closed Brayton cycle in one of our old helicopter test beds down at Bristol. And obviously, this is not designed to be physically representative of the size of the space micro-reactor, but as an example of, in our kind of agile development process, trying to knock over some of the concept killing risks early. So here we were trying to demonstrate the ability to control a closed cycle and the ability to control an inert gas working fluid, which, as I said earlier, obviously all of our gas turbine methods are based on air-breathing engines, and so using something exotic like a helium-xenon mixture or even a nitrogen mixture, which is kind of air-like but not quite, is quite novel. So the team in Bristol did a fantastic job of creating this rig. It was developed over the course of 12 months using commercially off-the-shelf equipment primarily, which is why it's so big. The turbo generator unit, we looked at around what was available, and I actually realised that what we were looking for was almost exactly the same as a Formula 1 MGUH unit, and that's what we did. So we spoke to a friendly Formula 1 team and we got an MGUH. You can see just on the bottom left-hand corner of the picture the back end of that unit. And that's just an example of the way we tried to work in this initial phase of the programme. It allowed us to demonstrate that we can successfully control the closed cycle and the makeup of the inert fluid. Really key in the overall programme, as I said earlier, because NASA have focused a lot of their power conversion work on Stirling engines. And actually there isn't a lot of research in North America on Brayton cycle or gas turbine converters. So we see this as being one of our real strengths in the UK, and obviously Rolls-Royce for a gas turbine company. And the event you can see here is, we ran this in February, and we had people from NASA Glen over, NASA HQ, and some of the commercial space operator customers to come and see this rig to understand what we've done and to show that it's possible, with a view to developing this into a real UK capability as part of the overall Artemis program. Okay, there we go. So just this is not the finished product. This is one of the work packages we did for the Space Agency was to develop a one-to-one scale model of the reactor core. We talked about the schematic of this earlier on. But there is a serious point here that this project is fantastic for STEM engagement, right? So this model was developed for the Space Agency. We've used it at conferences and schools, college events all over the country to try and generate interest in engineering, science, technology, maths subjects. Also great for us obviously to talk to our customers and end users, because having something to show them and for them to play with is somehow, having something tangible somehow moves people's minds forward. There we go. So that was Micro-Reactor. I've just got a couple of slides to talk about career opportunities for people that are interested. So I joined Rolls-Royce with the Graduate Development Programme back in 2006. Fantastic programme. We also offer internships and we also offer direct entry roles as well. The different schemes are slightly different structures, as you can see there. The Graduate Development Programme has different placements. You do 3 or 4 months in a role and move on to another one and do 5 or 6 of those over the course of the programme to develop breadth and then move into a permanent role after that. So internships, we offer 10-week internships over the summer and 12-month internships as well. You can see there some of the different kind of topics that people go and work in, and the different parts of the engineering organisation that people get experience in during that scheme. The key thing from this slide is the deadline is on the 22nd of November. So you don't have a lot of time if you have a quick application for it. But if anyone's interested in that, come and have a chat afterwards, and I can give you some more details. Okay. These slides talk about early career. I already talked about the University Technology Centre we have here and some of the opportunities we have for postgraduate students as well, and supporting things like NGD. So that's really done on a business-by-business basis within Rolls-Royce. But again, if you're interested in that, please come and talk afterwards. Okay, there you go. So I'll finish with a vision for the lunar base with our UK astronaut there on the bottom board. Thank you very much.